All right, so guys, what I'm going to do today is I will go over a couple of examples, two, maybe three examples related to base excitation, what we covered in the first class of this week on Monday. And I'm also going to show you how to model a base excitation, a system under base excitation in OpenModelica. Right? So because that's what you need for your project, you have to model that base excitation in OpenModelica, and that would be a good guideline for you to do the modeling for your project. Right? So let's just start an example first. Example. So we have a here we have a 35 kilogram, a 35 kilogram flow monitoring device. Let's say this is some kind of fluid mechanics lab monitoring device, which is placed on a table in that lab environment, in the laboratory. That's what it is. In the laboratory. In the laboratory, right? Now a pod of stiffness 210 to 5 Newton per meter and damping ratio 0.08 is placed between the device and the table. Right. Now we are said the table is bolted to laboratory floor. The table is bolted to the laboratory floor. Said also measurements indicate that the floor has a steady state vibration amplitude of 0.5 millimeters at a frequency of 30 hertz. Sorry. Now the question is, what is the amplitude of displacement of the floor well, not of the floor, of the flow monitoring device, monitoring device. All right, so the story is we have a table. I'm going to try to draw it here, something like this. Let's say that this is the table and it's bolted to floor, so let's just do it this way. This is the floor. Let me change this. This is the floor. This is the table bolted to floor. Now we have some flow monitoring device, whatever it is. Let's just put it somewhere here. And then there is a pad between this device and the floor. Let's just draw the pad there. Some kind of padding to add some damping, to absorb the vibration a little bit coming from the floor. Now, we did some frequency sweep or excited this structure on the specific frequency 30 Hertz and measured the steady state vibration amplitude of the floor. So think about this way. The floor oscillates, it's the oscillation of the floor. And because of that, the table oscillates, which is in this case is assumed to be very rigid. So whatever is the vibration of the floor would be the vibration of the table. And we have this flow monitoring device there that we want to study. Right? So if you look at this whole system, if you think about this pad as the spring damper, which what it is, right? We can model a pad. We are given its stiffness and we are given its damping ratio, meaning that think about this pad as an equivalent system in our basically within the scope of our course, right? When we are given the stiffness and damping of this pad, it means we can actually model that as a spring and damper. Remember, I said pretty much everything around you, you can model it as a series, as either one or a series of spring and dampers and masses. This whole idea, even about the finite element modeling, if you look further into theory, you will see that we actually that's where we start. We can look at them as a series of masses connected to each other with some stiffness and damping between them. But it's a whole new story. All right, so this is the flow monitoring device. Now here is the spring. I can do better spring. All right, let's do this as a spring. And here is a damper. And this is the base. And the base is moving. The base would be the floor and the table, which is bolted to a floor and it's rigid. So it has a mass, it has some stiffness, it has some K. Now, let me just make it more similar to what. Yeah. So this is moving, right, with some YT. And we want to know what is this X T. Well, specifically speaking, what is the magnitude of that motion? So pretty much what we're given is a base excitation. Now let's see what we have. We have the mass, 35 kilogram. We have the stiffness for that spring, which is 2 times 10 to 5 Newton per meter. We have the damping ratio, zeta, which is 0.08. Now, what else do we have? This is one set of information there. We also know that the floor has the steady state vibration amplitude, look at here, of 0.5 millimeters. What is that? When we were talking about base excitation, what parameter is this? Can someone tell me? Remember, YT, let me put it here. YT was Y sine omega B T. Right? Some input harmonic excitation to the base. Can someone tell me what is that 0.5 millimeters and what is that 30 Hertz frequency? Good to know. All right.
Is 0.5 millimeters the Y and the 30 hertz is the omega B?
Yes. Thank you, Michael. You returned the hope. Uh, so Y, right? If this is the amplitude, the steady state vibration amplitude would be Y, as Michael said. So I'll put it here. Y would be 0.5 millimeters because that's how the floor is moving. We are given the steady state vibration amplitude. Now, keep in mind when we say steady state, when we studied the base excitation, we were only focused on a steady state response. We said we don't really care about transient response. We did not take into account the transient response. Go back to force vibration of a system with viscous damper. We studied the whole response. Remember, transient plus steady state, and we said the whole response is a combination or mix of or superposition of transient and steady state. But when we studied base excitation, we said, well, let's put aside the steady state, put aside the transient response, and just be focused on a steady state response. And everything we found and calculations we did, all the results, transmissibility, displacement transmissibility, the ratio between excitation frequency and base excitation, the frequency of the base, so excitation frequency and the natural frequency, the force transmitted to the structure, they were all about steady state response. So that makes sense that here we are talking about steady state vibration amplitude. And the frequency would be, well, omega b. Well, we use omega to show frequency in radian per second, and here it's 30 hertz. So let's just put 30 times 2 pi, right? Converting it into radian per second. All right. So I know y, I know omega b, zeta is given, m and k are given. What am I looking after then? I'm looking after the amplitude of displacement. Now remember, the response also was x, well, the particular response or a steady state response was x cosine omega t minus some theta. And that amplitude of displacement of the flow monitoring device would be the x you're looking for. Keep in mind, in these problems, in these situations, usually the main challenge is to identify the parameters correctly. Once you do it, the rest is just you have the equations, you have just plug in the numbers and do the math. That's pretty much it. So transmissibility, it means I'm looking for transmissibility, displacement transmissibility. If the base is moved y amount, how much the mass m is going to be moved. Remember, we are talking about that plot, frequency ratio versus displacement transmissibility, which is a very important graph. It tells us can we reduce the vibration in the moving mass when we have some specific base excitation. That is the whole idea of vibration isolation, right? We are isolating the vibration. We are making sure that when some base is moving with some specific frequency and amplitude, right, whatever we have on that base, in this case, this flow monitoring device, we want to, in most cases, we want to reduce the amplitude of that vibration. Make sure that for a huge vibration that we have in the base, our device, flow monitoring device, is relatively stable and it's not moving that much, or it's moving much less than the floor. So we're isolating the vibration of the floor, taking it away, making sure that it's not transmitted to the mass, or to, in this case, it's not transmitted to a flow monitoring device. So, the whole idea of displacement transmissibility. TD, displacement transmissibility, was x over y, right? And it was the square root of 1 plus 2 zeta r squared. Well, not exactly that way. 2 zeta r squared, and this goes all the way down, over 1 minus, I don't know why I'm typing. Let me just do the whole thing again. All right. Square root of 1 plus 2 zeta r squared divided by 1 minus r squared squared plus 2 zeta r squared. Now, what do I need to form this? Well, I have y already. I have zeta. I'm looking for x, and I know y. So what am I missing? What do I need?
R.
Yes, exactly. I'm looking for r, right? R, and I can calculate that. All I need to do is, remember, R is omega b in this case, frequency of the base over natural frequency. Thank you, Zeri. Omega excitation frequency or natural frequency. So excitation frequency, I have it, it's 30 hertz. Natural frequency, well, I don't, but I can calculate, right? It's I have mass and a stiffness here. Right, so omega n would be square root of k over m, which would be square root of k, which is 2 10 to 5, divided by m, which is 35 kilograms. If you do that math, you should get, or hopefully you get, 75.6 radian per second. That would be natural frequency. So once you have natural frequency, I'm going to put it here. R becomes omega b over omega n, right? R was ratio, frequency ratio. Omega b is 30 times 2 pi, and omega n 75.6. So if you do that math, you'll get, I think 2.49. That's no unit. It's frequency over frequency. So now I have R, I have zeta, I have y. I can just find x from that equation. Right? From there, if I take it down to here, x, well, let's just write it this way. X becomes y square root of 1 plus, well, 2 times zeta, which is 0.08, times r, which became 2.49, right, squared. And at the bottom denominator, we have 1 minus r squared, which is 2.49 squared. Squared plus 2 times zeta times r squared. All right, from there, and remember y is also 0.5 millimeters, so 0.5 times to minus 3 meters. From there, you can actually find x, right? X would be, let me write it a little better. X would be, what I got was 0.03 times 10 to minus 4 meters. And here's what we were looking for. We were asked to find the amplitude of displacement of the flow monitoring device. And this is x, the amplitude. Let me separate things a little bit here. These are like, this is the general model I put together. And then the rest is the solution. All right, so what does this tell us? It tells us that if the base is moved, if the maximum amplitude or motion of the base is 0.5 millimeters, the amplitude of the motion for the flow monitoring device, or the maximum amplitude of the motion, would be about 0.1 millimeters. So the vibration of the base, because of the spring and damper we put there, we are isolating, we are taking away part of the vibration coming from the base and making sure that not all of it is transmitted to the mass or to this flow monitoring device. So it's very practical when you're designing something and you want to make sure that, well, whatever is the vibration of the environment, I don't want my device to be under that much vibration. My device cannot handle that much vibration. So if I have some estimation of what is the maximum vibration in this specific environment, right, I can design a system using some spring and damper. I can move around and find the optimal spring and damper values or spring stiffness and damping constant for this system to make sure that the motion of my device, in this case is flow monitoring device on this table, does not exceed some specific value. Right? In this case, we see the maximum for maximum value, maximum input vibration of 0.5 millimeters. My flow monitoring device is going to move only 0.1 millimeters. So much less than the vibration of the floor. How do I do it? I use a combination of a spring and damper. Now, let's model this in OpenModelica. That's not what I want to do. Let's see how can we model this base excitation there. I have my OpenModelica open. I'm going to create a new model. And let's call this I guess base excitation example. Keep in mind when you're putting a name for OpenModelica models, do not use a space from experience. You have to put under either underscore or just connect all the words together. Nothing selected here, everything unchecked. Click on OK. So I'm gonna get into my new model. I'm gonna save this somewhere. Let's put it on exam desktop that I have, base excitation example. Now it's saved. Either save it with this or go to File and use Save. Now let's go to, now you have it in your tree libraries browser. You also have your model there. So if I open Modelica library, go under Mechanics, go under Translational, and go under Components. Right. Now the components I need, obviously I need a mass, I need a spring damper element. Right. These are established in this system. Let's call this mass. I'm gonna make it a little bigger and use Control R to rotate it so it's upward. The arrow is pointing up. I'll bring a spring damper, drag and drop it here. Let's just call it spring damper. Make it a little bigger. Control R to rotate it, make sure the arrows are in the same direction. All right. So this is my mass, this is my spring damper. What else if I go back? I have a mass, a spring damper, then I have some base that is moving. So I have some input signal, right? That YT, Y sine omega BT. So I need some block that can generate that signal for me, right? So for that, I'll go to, let me close mechanics. So it's less crowded. Go to blocks. I'll go under sources. Since it's a sine input, I'll just use the sine function. I drag and drop it here. Let's call that input excitation. In this case, it's a base excitation. Make it a little bigger. I turn it around multiple times, Control R, and now I have it. All right, the next part of this story is that how am I supposed to tell this software that, well, this is the input signal, but interpret that input signal as a displacement. Remember, we are applying a displacement. The base excitation is a type of force vibration, but the difference between this and force vibration on a spring mass damper are two differences. First one, over there, spring and mass are connected to a fixed floor, and the force is applied on the mass. So the input is force, harmonic force, and applied on the mass. In a base excitation, we have a spring. We still have the same spring and damper and mass those elements, but in this case, we have the input applied to the base instead of the mass. So base is not fixed, and the input is a displacement, imposed displacement, which is in our case is a harmonic function. Right, so I have to tell the software this signal that is I'm inputting to my system, it's a displacement, not a force. How do I do that? Well, I close the blocks, I go back to mechanics, right? Close sources. I go to sources under mechanics translational, I would say address, right? In library browser. I go to mechanics, go to translational, open sources. And sources, remember the last time when I modeled the base force vibration, I used the force block. So the input signal was interpreted as force. Now I'm using the position block. Just called it position. So the software interprets the input signal as a position displacement or as a displacement, change in position, not a force. I'm just going to use Control Alt multiple times, rotate in the correct direction. All right. Move it all up. Move this all up. All right. So let's connect things together. I can left click on this, drag, and then left click on this, the port on spring damper, go from the port on the spring damper, connect it to the port on the position or the connector here in this case. And then left click on the input port on that and the input port, output port for the physical signal, and click again. So now I can move things around a little bit to make sure that things are connected. Sometimes they don't really connect properly. All right. So this is my model. This is the model of a base excitation for a system with just one mass and a set of a spring and damper. If I go to mass, let's plug in the values. My mass for this case was 35 kilograms. And I leave everything else. Remember, we just talked about steady state response. So you will still have the option to give some initial values for initial displacement and initial velocity, because this model is going to calculate the response of this system under base excitation. Now, the response includes both, you'll see, transient response and steady state response. But what we are interested and what we studied when we were doing when we were following the analytical solution is just a steady state response. So we have to ignore the initial phase that the response of the, in this case, flow monitoring device or the mass is not steady yet. I'll just leave this empty, because if you leave this empty, software is just going to assume some number. But you can, if you want, you can just plug in, go to true start value and give 0 if you want. Maybe it's a bit of practice to give some number instead of leaving it empty. Now here I have to plug in the spring constant, which I have it, right? It was 210. If you go back, it was 2 times 10 to 5. So I'll put 2E5. And the unit is Newton per meter, so I'm good. I need to find damping constant. I do not have the damping constant here, right? But I do have zeta, which is damping ratio, and I have M and K. Right? So I can actually calculate the damping constant for my modeling. You can just pretty much say, well, zeta is equal to C over C critical, which is equal to C over 2 square root of MK, if I'm not wrong, hopefully not. C would be 2 zeta square root MK. Or you could also put 2M omega N. Right? It's the same. So that would be 2.08 square root of M, which was 35 kilograms, and K was 210 to 5. If you do this calculation, you'll get the damping value of, if I did it right, please double check, 423.6 Newton second. Well, Newton second per meter. This was not part of the problem, but was asked. But in order to model the system, I had to actually calculate the damping. But now I have C, damping constant. If I go back to my Modelica model, keep in mind I said C and D are replaced here, so don't get confused. In the software, C is the spring constant, which is OK in your course, and D is damping constant, which is C in your course, which makes it very tricky. So C is the damping. Always look at the unit. Spring constant. The explanation in front of it. So spring constant from this example. Damping constant. I got 423.36. The unit is correct. So 423.36. Double check. Yeah. All right. The rest, just leave it empty. There's nothing to worry about.
Dr. Masood,
Yes. Go ahead.
we don't need a cosine function connected to the mass because there's no force being applied to it, right?
Yes. So the force is not a force vibration anymore. It's a base excitation, right? So before, for force vibration, we're applying the force to the mass. Now we are applying the imposed displacement to the base, right? Here is our base, basically. If you want to think about it that way, this is the system, right? This is our base, and this is the imposed displacement to the base. So that's our YT, and whatever it moves would be your XT. Does that make sense? Hopefully it does.
Okay, thank you.
Remember, before what we had, guys, was modeling the same system. We had the mass, we had the spring damper block here for force vibration, right? We had this. We had the spring damper block there, and this part was fixed. I used some fixed, and the input still was a signal, but instead of this connector that says position, I used the connector that was for the force. So I was telling the software to interpret the input as a force. But now we're dealing with the base excitation, which is some imposed motion on the base. All right. Now the input excitation, what we have there? We have the amplitude. I'll go back to problem. We have the amplitude of 0.5 millimeters. So I'm just going to put 0.5 e minus 3. The frequency of the input excitation, well, the unit is hertz, so good for us. We have that as 30 hertz, so directly plug in. There is no offset in term or a starting time different from the time equals to 0. So I'll leave those empty, which is 0. That's pretty much this models my input base excitation, right? This models my YT. This is YT. It's called Y here, so it's good. All right. If everything is fine, let's see how it goes. Click on OK. Let me check my model. Check the model. It says I have 25 equations and 25 variables. Those are the same numbers, so should be good. I go to simulation setup. I say, well, let's just start with 1 second, and I'll show you what happens. 1 second, and let's use 1,000 points to plot. I click on OK. You get some warning because we didn't really plug in the initial values for a couple of parameters, but we'll be fine because we're not really interested in transient response anyway. Remember that the software is solving the code that it put together for the system. Now we went from modeling tab to plotting tab. Over there, I can take a look at the motion of the mass, CS. Now this is the displacement of the mass, right? This is xt, but not xpt, steady state. This is whole xt, which includes the transient response and steady state response. If you remember, we said, well, x t includes xht, which is harmonic response of the harmonic part of the differential equation, and xpt. And we said this one is the transient response, meaning that it happens at the beginning of the motion, and this is the steady state response. Now you can actually see it here that we started to have some transient. Right? Transient is happening, let's say, at the starting from the beginning to somewhere, maybe by just looking, and you still see the effect of transient even up to here a little bit, maybe even further less. So this part approximately could be the transient response, which we did not calculate using our analytical model. Whatever happens after is the steady state response. This would be my transient response. Now let's see if we can make sense out of this. So again, we are looking into transient response. I'm not that interested in steady state response. And imagine and think about it. The farther you go, the less the effect of transient response, and it's gone, as it says transient. So here I'm going to do this. I'm going to go back to my modeling, and let's just change this to start time from 1 second. So I don't care about the beginning of the motion. And let's just model this to 1.5 seconds. For 0.5 seconds, but forget about the beginning, right? So I don't even have to look at it. But you have to model the system from the beginning, from 0 in the first attempt, to see where is the transient response and get a sense of, oh, it seems like transient response is disappearing at this point. It has no effect on. Now, when we zoom in, you still see that we have an effect, transient response. Right? Let's do this. If I plot, right, I'm plotting the mass, motion of the mass, xt. I can also plot yt. Right? Here is the input that we applied, which makes sense, right? This is the input we applied. This is, let me use the same color. This is yt. And this one is xt. Right? Now you can even see by looking at this, while the ground is moving with 0.5, here is your x. Not the right color. Here is your x. This is your x. And maybe somewhere around there, if at this point is a steady state response. I don't know if I can draw a straight line from there. Let's see if I can. Challenge accepted. I failed. It's not that steady, but there you go. This is, sorry, that was your y, and this is your x. Somebody should stop me. This is your y, since the maximum amplitude of your input. And this is your x. This is your x, the maximum amplitude of your base motion. So you see that there's a big difference. While the ground is moving about 0.5 millimeters, my device is not moving that much. It's moving much less. I show you around what we found. It's around, if you look at this, what is this? If this is 0.002, this is 0.0001, which is 1 millimeter, which is about 0.1 millimeters. So if the ground is moving for about 0.5 millimeters, my device is moving just about 0.1 millimeters. So I could successfully, whatever this design was, whoever designed this could successfully get rid of a lot of vibration and did not allow that vibration to transmit to my device, which I'm trying to protect from vibration of this ground. Right? Now, if you want to get a better sense of steady state, and if you don't want to see the transient response at all, let's just go even farther. Let's go back to model, and let's go. Why not? Let's go from 10 to 10.5 seconds. Well, let's just model this. 1,000 points should suffice. So I'm saying this. I'm telling the software, you know what? Don't start from the beginning. Start from 10 seconds after the motion has been happening. Hopefully that works. Oh no. All right. I have to scratch that part. Whatever I said about this, I forgot that. That would be a difficult thing to do, I know. But do not start the simulation from from any given point, because I forgot about this part, that this software assumes that the motion starts at t equals 10 seconds. So no matter how far I go, it's assuming, well, nothing was happening up until 10 seconds. And then suddenly at t equals to 10, I start applying the impose. So you always are going to see the transient response, no matter what. Hopefully that is not going to stick, what I said and emphasized in terms of modeling. In terms of software, the stories is still the same. You see the transient response here, and then you see almost up to here even maybe, and slightly you see the steady state response. Transient response disappearing. But the software now is starting the simulation from t equals to 10 seconds. So we can't actually, I forgot about this. I apologize for that. We can't actually start the simulation from 10 seconds. Well, we can start it, but that tells the software that the imposed displacement is applied at t equals to 10 seconds, not that do the simulation for 10 seconds and just show me what you have from 10 to 10.5. So you have to basically keep this always on 0. And let's do 2 seconds or 3 seconds. And I'm going to use more points so I get a more smooth plot. I'll show you how to get a better view of just your steady state response by just moving the plot instead of playing around with the simulation time. So again, mark my word, remember that. Do not play around with the simulation time. So this is a pretty long simulation time. It's not that easy to see what's going on. What you can do is that, well, let's say you want to just see the simulation after 1.5 seconds or from 1.5 to 2 seconds. So go to setup and change the range for X. This is a much better approach. 1.5 to 2 seconds. If I click on that, now I only get a portion of the response. Now it's here you see you have a better idea of what's going on. Right? This is your input, YT, and this is your output. Or that's the motion of the base, and this is the motion of the in this case flow monitoring device. All right. Keep in mind, this is not, I didn't do all the process. When you want to represent the plot, make sure that you change the titles, put vertical axis title, change, put the units, put legends. If you have more than 2 variables, change the name of the variables. Mass.s doesn't make that much sense. You can just put that as xt. Right? Input excitation, I can just put it as yt. If I can use different line size, I'm just use 0.2 and do that also as 0.2 or 2 thickness. So now I have a better legend. Right? I can just move things around. Let's say you don't want it, you just want it on the right, on the bottom. I prefer to just keep it at the top. And put the label for y-axis, right? Let's say the amplitude in meters, and this is time. Whoops, not that. Time in seconds. So clear your plot, make sure everything is there, and then you can always save it. You can save the plot as a, go somewhere, you can just save it as a PNG file and use it in your reports when you're doing the simulation for a basic citation. All right. Any question about this, folks? What we did, hopefully this helps you a lot about for your project, because pretty much you have to model a basic citation there as well. Okay, and just close this. Any question about the example and the way we did it in Modelica? All right. Just remember, again, my bad, you should have paid attention to that. Simulation time always start from 0. Right? But keep in mind at the beginning, you're going to have some transient effect that you can just safely ignore that in our case when you are comparing your results with some analytical solution we derived in this course, because we only focus on a steady state part of the response when we were talking about base excitation. We did find the system response under force vibration, the full response, including the transient response. But for base excitation, only a steady state response. All right. Let's take a look at another example. A little different. This one, let's put it here. Example. This is more related to, well, in this example, it's trying to talk about the landing gear. So it says the landing gear of an airplane can be, yeah, that's a good word, idealized as a spring mass damper system. As a spring mass damper system. If the runaway surface is described by yt is equal to y naught sine omega t, find the value of damping constant that limits the amplitude of vibration of the plane or airplane parentheses x to 0.1 meter. Consider the following, which is m is equal to 2,000 kilogram, y naught is equal to 0.2 meters, and omega is 157.08 rad per second, and also you're given the value of k, which is 5×10⁶ Newton per meter. What's the story? Well, a very, very, very simplified model of a landing gear. Oh, not very, very, very. Maybe just very, or maybe two varies. Right? So too many. Let's think about it this way. You have whatever is on top, the structure, which the distribution of the mass on this specific landing gear. They say let's take it 2,000 kilogram. Right? So I'm just going to put the mass there. Then you have some landing gear, some structure there, some housing with struts and viscous dampers, which can be modeled as a spring and damper. So we'll just model, if I can draw it. And they're like connected to some set of, let's say, tires. It's a very bad drawing. And then basically what happens is that we have some runaway, that's some surface that we can ideally model that using YT. So think about, I don't know if you watched the video about the car when they were designing the spring and damper, they were explaining how a spring and damper can absorb the vibration or isolate the vibration. That's pretty much very similar to this, right? We are designing a vibration isolator, right? Trying to isolate the vibration that is applied to the base from the surface, from the ground, from the road, and isolate that, make sure that it's not transmitted to the structure. Now, this is the landing gear. That one was for a car. This is the landing gear of an airplane. Now we have all the parameters, right? We have m is 2000. I'm not going to write it here actually, it's already written there. So we have m 2000 kilogram. We have y naught. Remember, this is the input vibration, input imposed displacement to the base. Right? This is pretty much can be modeled as, right, spring and a damper and a base excitation. Now you see how important base excitation is and how much you're going to see it everywhere, or in a lot of places when you're designing things, especially in mechanical engineering when we are typically trying to isolate and get rid of the vibration coming to the system from one direction or another. We have omega. In this case, this is omega B, right? This is omega B, the excitation from the base. And this is K. So let's take a look at transmissibility, right? We are given Y, this is our Y, and we are given X. We are told that we don't want X to exceed this value, XT not to exceed this value. So this means that this should be the maximum amplitude of XT, which is up capital X. Right? Since XT was X cosine omega T minus theta, this X, well, this is XT. So we don't want this to exceed this value, that value. This value would be my maximum amplitude then. All right, so take a look. Let's see what we are missing and what we need. Transmissibility, right color. Transmissibility is X over Y, which is a square root of 1 plus 2 zeta R squared over 1 minus R squared plus 2 zeta R squared. Now, we are given the value of mass and stiffness, so like similar to the previous problem, we can actually find natural frequency and find R. So K over M is the square root of 5 10 to 6 divided by mass, which is given somewhere, or 2000. If you do this math, you're going to get, well, actually you're going to get 50 rad per second. So R would become omega over omega n, right? Omega B, if you want to put it that way. The frequency ratio is 1.57.08 divided by natural frequency, which is 50. So we'll get 3. Oh, I forgot. 3.1416. That's no unit. Now, what do we have in this equation? We are given X. We know what Y is. We know R now. Now we have to find zeta. The story is all different. Because we are designing a structure, we need to find the value of damping constant. Keep in mind, find the value of damping constant, C. To find C, we have to find zeta. So in this equation, we have everything except zeta. So we can actually solve that for zeta. If I do that, I'll get X squared is equal to Y squared times 1 plus 2 zeta R squared divided by 1 minus R squared squared plus 2 zeta R squared. Now plug in the values, plug in X as 0.1, Y as 0.2, R as, I'll just show it here, R as 3.1416. Move things around, I'll just give you the final answer, or at least closer to final answer. Move things around, right? You square things, multiply the values. You're going to end up getting a second order equation, or at least I would say, yeah, it's a second order, but it's easy to solve. Equation for zeta. You're going to end up getting something along this line. Hopefully my number is right. 1.83316. Zeta squared becomes 0.746698. I'm not sure why they go with that many digits. So this one from there, let me, you can find zeta. It gives you two values, one positive, one negative. Obviously, zeta cannot be negative, so you can just get the positive value, 0.794. That would be your value of zeta. So still doing the same equation, the unknown has changed now. We are designing that. Instead of given the value of damping, we are given everything else, and we're given what is the design constraint that, well, this should not move more than 0.1 if the input, maximum input is 0.2 meter. So once you have zeta, the rest is pretty straightforward, right? Again, the same story. Zeta is equal to C over C critical. Let me write in this time as 2m omega n. So you can find C is 2 zeta m omega n. Hopefully my calculations are correct. You know zeta, you just found it. M is given, omega n, you found it as natural frequency. You just do the math. You will find 158,873 something. So I think 74 Newton second. So here is the answer. The damping that you need to install on this system, the viscous damper with this damping constant that you need to install on this system to make sure that the structure, whatever it is not moving more than 0.1 meters as long as the maximum input amplitude imposed by this surface, or because of the vibration of this vibration applied to the system because of the uneven surface of this runaway, the maximum amplitude is not more than is 0.2. Let me rephrase that, probably say it in a bad way, but as long as the maximum amplitude of the excitation is 0.2, the maximum amplitude of your structure is not going to exceed 0.1 as long as this damper is installed. All right. And keep in mind, let me just bring that graph if I can find it somewhere. I can bring it here. Different course. So if I go to right course, I can find what. Keep in mind, this is what we're looking at. Right? It's frequency ratio R over transmissibility, displacement transmissibility. So what was R? R was 3 point, I think I don't have it here. 3 point somewhere all the way the line there. Somewhere there is R for this problem. 3 point, I forgot that.
3.16.
Thank you. 1416. Thank you. 1416. I'm going back and forth. I think I'm giving you guys a headache. All right, so this is R. So some zeta that you found, zeta is 0.7. So for if you plot it, it's somewhere there, somewhere here, 0.7 something. So for some zeta, maybe this case comes all the way, gets here. This is the transmissibility. Transmissibility gets to 0.5. What does that mean? It means if you use this damping constant and you get this damping ratio, transmissibility is 0.5, meaning that I think it becomes 0.5 because for a given y, for a y of 0.2, you get this maximum amplitude of 0.1. Does that make sense? If it's 1, you get the same amplitude. If it's more than 1, you get more vibration in your structure than your base. If it's below 1, obviously we get less. So 0.1 means we reduce the vibration to half, vibration coming from the base. All right. One more example, very quick. Just want to show you what happens in a structure and what if, you'll see how much your life is easier if there is no damping with that assumption. Any question about the previous example while I'm writing this? All right. So I have a single story building. This goes back to stiffness. Building frame. A single story building frame is subjected to a harmonic ground motion of yt is equal to 0.1 sine 2t. Now we are asked to find the building displacement. Building maximum, building maximum displacement amplitude. Now it's also given you have this. Well, let me delete that. You have this as the building connected to the floor using two columns. This is part of the problem given to you. Like this. And here is your ground or the base. Well, this base is moving. Wait, yt is 0.1 sine 2t. This is the mass m, and you will have to find this building maximum displacement. Now, the trick here is you have to pay attention. Remember when we were talking about cantilever beams. Here is that they come handy. It actually, in laboratory scale, they do a lot of testing like this, just as simple as this. Just putting two columns, the structure, and model the general behavior of a building. So it's not a weird assumption or unusual assumption to make. Now, think about it. When this moves, right, we're going to have a cantilever beam here that is, let's say, if it's moving to the left or for some reason it's moving like this at some given moment. This is going to be the motion. It's going this way and then comes back and goes this way. This is nothing but a cantilever beam. Same story about this one. So, as easy as that, I can model this as this mass there. I have two spring, K1, K2, and some base that is moving now this way. Pretty neat. It was in this direction, y is moving and x is in this direction, so both of them are in the same direction. I'm modeling the motion of the tip of the cantilever beam, which is connected to this mass using a spring. And we know that from before. Right? We said, well, when we have a cantilever beam like this, and it has some bending, it's delta, the motion of this, I can replace the motion of the tip of the beam with a spring. And you can go with E, I, and L for this, E, I, and L for this. So I'll use what I was doing. K1 is equal to K2 is 3EI over L to 3. So the equivalent of damping stiffness would be two of these. Or just, these are in parallel, right? These are in parallel. So I just sum them up. There you go. This becomes 6EI over L to 3. So this is pretty much just the mass, some base, K equivalent, and it's moving with YT. I want to know what is xt is equal to x cosine omega t minus theta. I want to know what this x is. Like the maximum amplitude. How do I find it? Well, transmissibility, TD. You'll see how things become much easier, because once there is no damping, TD is x over y is the square root of 1 plus 2 zeta r squared over 1 minus r squared squared plus 2 zeta r squared. Now in this case, I have no damping. So this term becomes 0, and this term becomes 0. So I can just take x, easily just say x is equal to y, 1 over 1 minus r squared, then squared, right, can come out of this square root. This becomes, I'm going to write it this way. Yeah, maybe just this. Becomes 1 over 1 minus r squared. And you can keep it in absolute value because we're taking it out of the square root. So it's pretty much this. Y over 1 minus r squared. That's it. We have a relation between x and y. All I need to do, keep in mind, I'm trying to find x. So all I need to do is just find r. And r is also easy. Omega n is the square root of k equivalent over m. I didn't give any number for this. So 6ei over m L to 3. And omega input. What is omega input? Here is omega input. This is omega b. So this is omega b is equal to 2. From there I can find r. Omega over omega n, or omega b over omega n, would be 2 over square root of 6ei over m L to 3. And from there you can actually simplify this a little bit. This goes up, it becomes 4m L to 3 over 6ei. This is equal to. So knowing r, you can plug in there and just get the expression for x. If you do it, x becomes, let me go back, y is 0.1, yes, that I remember, divided by 1 minus, well, r squared in this case was 4m L to 3 divided by 6ei, right? That was r I found. Plug it into this equation for x, right there. And I got my x as a function of the stiffness of those columns, the length of those columns, area moment of inertia, right, for cross section of those, and the mass. I can further simplify this if you want. I think we're going to end up getting 0.6 EI divided by 6 EI minus 4 ML to 3. If you were given numbers, you can just plug in. But this is X. All right. Just wanted you to see that if there is no damping, right, there's still the same equations apply. You know, the same equations we got can be applied, especially in terms of a structure. You know, you see these in actually laboratory scales. And again, the video I shared with you about resonance and base excitation, remember, this is pretty much what they were doing. They had some kind of building or a model of a building, 2 columns. You could actually analytically calculate. Given the base excitation, you could find what is the motion of that mass at the top. And again, same equation, just get rid of zeta because there is no damping in this idealized situation. All right.